Welcome back, Recalc. Lesson 1.4, we're going to be looking at graph transformations. In fact, just single transformations as we introduce or actually kind of review a little bit of this, which is material from previous courses. So out of all the transformations that we have, we have reflections, we've got translations, and then we also have our stretches and our shrinks. So overall, what we should be able to do is we will take any graph, move it up and move it down, that's a translation, stretch it or squish it, and flip it upside down. That's a reflection. And also add flip it sideways. And that's what we're going to look at first. Reflections, those flips. So if we were to start with any function, y equals any old function, in general, the rule is that if we flip it across the x-axis, we're going to just negate the whole function. So this one against flipping across the x-axis. If we're going to flip across the y-axis, what we'll have is y equals f of negative x. And that's just putting the opposite inputs in. So let's explain it. Let's just get through an example here and then have you do a little practice and talk about those just to kind of see how it works. So what I can see over here in example number 1, here's my first function. And by formula-wise, if I look and kind of compare it to over here, I should see that from the parent function, if I look at this, the parent function of this function is y equals the absolute value of x. That's the basic function of this. And you can see we're just negating that out front. So what that should do is it should flip it across the x-axis. Okay, so normally, we see that our absolute value function would make that v and would be something like this. They come through, and it's always that slope of 1 there, so it'd be up 1 over 1, up 1 over 1, or in that fashion. So if I look at what the transformation here, okay, I look at maybe just making a table of values here, just making an XY table. And the original function, the original parent function here, so this original parent function, if I had it, and if I look at some points, if I put 1 in, I get 1 out. If I put 0 in, I get 0 out. If I put negative 1 in, I get 1 out. And that's where I had those points. I've got 0, 0, I got the 1, 1, I've got the negative 1, 1. That's what graphs this one. So I think what I'm going to do actually is change this just to colors so we can kind of talk about that a little differently. And we're going to look at the transformation that's going to happen. Now, what should happen, according to the rule here, is the transformation should be a flip across the x-axis. So kind of looking at a table of values, you see that it does that. So if I'm picturing this ahead of time, I should think that this graph should flip upside down. It should be down over here in quadrants 3 and 4. Let's just double check with the little table here. We have a little XY table. And usually the same starting values here. I'm going to put in 1, put in 0, put in negative 1. But now I'm putting it into this function. Okay, so I put 1 in there. Absolute value is 1, make it negative is negative 1. And put 0 in there, well, it's going to still say 0. Put negative 1 in there, it's going to make it positive, so it's going to make it 1, and then make the negative out front, this would be negative 1. So if I plot those points there, I got 0, 0, I have 1, negative 1, and I got negative 1, negative 1. If I were to choose more points, I could see that as well, and that it in fact does just flip it across the x-axis. So I'm going to go through these guided practices with you. I'm not going to have you pause the video right now. I'm just going to kind of work through those right there with you. So if I look at this is the natural log function. Our parent function will be y equals the natural log of x. And remembering what that function looks like, we can draw it on here. If you want, you can draw yourself a little xy table as well, just to help support. And I'm going to kind of choose some convenient values here for natural log. I know that if I put 1 there, the natural log of 1 is 0. Another kind of convenient value is e, because I take the natural log of e, that's 1. So again, I'm just drawing the parent function. So I know natural logs kind of come up and curve out like this. So I just take those 2 points that I've got. The first one's at 1, 0, which would be right here. And then e, 2.7, right here and up 1. So I know this graph is going to do something like this. Now, go back here and choose a different color. Looking at the transformation, I'll look at the rules from above up here. Okay, this one seems to be following that rule right there, because all I'm doing is negating out front the function. So by rule, the transformation here should be a flip across the x-axis. So you might want to look, just make a little table. But if I start thinking about this, it should flip across the x-axis. So I know this branch will come down and be over here, and we'll probably go up here, be asymptotic to that y-axis. So again, we're going to do the same thing, put the same values in, put 1 in, but now we're putting it into this function. So put natural log of 1, well, that's 0. Make it negative is still 0. If I put e in, natural log of e is 1, make it negative, we'll make that negative 1. So that's where I'd have the value is 1, 0, still have that one there. But then I'd have e, which is about 2.7, and negative 1 will be down here. So yeah, it is following that. It's going to be doing this. And then come on up like that. This one here, we can, again, we'll look at the parent function for this. That's again the natural log. So it's going to say it's y equals the natural log of x. So again, that's our coming in like this, hitting that 1, 0, and that E1 point like that, based off of what we just did over here as well. So let's go and look at this transformation. Again, by rule here, if you look at the rule, we're taking the opposite of the input value. So what this should do is this should flip across the y-axis. We can do a little proof here on that one. Make a little XY table. And again, use the same inputs that we used over here in guided practice 9a. Put in 1, put in E. And but now we're not, that's the x that we put in, but now we're actually putting that negative x in. So if we put a negative 1, a negative e in, we'll look at what the answer is. So if I'm taking, excuse me, negative 1, and putting this negative 1 in for this x, that'd be negative 1 would be positive 1, natural log of 1. Would be 0. I take and put negative e in, negative e be positive e. Natural log of e is 1. So if we look at these values, x equals negative 1, 0, that's over here. And negative e is about negative 2.7, and then go to 1, be right here. And that's where this graph will do that, which is a flip across the y-axis. Okay, so those are the formulas you should kind of remember up here on how to flip across the x-axis or flip across the y-axis. If you want a graph to flip across the x-axis, just put a negative in front of the function, whatever that happens to be. If you want to flip it across the y-axis, well, then you got to go and put negative x in for each of the x's in that function. Okay. Let's take a look at stretches and shrinks. Okay. So, we're going to look at our rules here, and it looks kind of complicated, but I'm going to try to get this straight for you here. And what I'm going to talk to you about is how to horizontally stretch or shrink things, and then how to vertically stretch or shrink things. So first of all, with the horizontal stretching or shrinking, that's going to be, you're going to be doing something, that's something right here to the inside of a function. Okay, so I like to say inside the parentheses, and that will change your horizontal stretch or shrink. Okay, so if we're looking at here and we're dividing by a number, okay, and in that c value is bigger than 1. Okay, so we're here dividing by a number bigger than 1. If that c value is bigger than 1, that c value is bigger than 1, what this will do is it will stretch it horizontally. It will stretch it out from left to right more. Where if that c value is less than 1, then it's going to shrink it. Okay? So we'll look at an example here in just a second. And because I want to put it together with these vertical stretches and shrinks too. So here for vertical stretching and shrinking, it's not inside the function, it's out front. It's out front of the function. And again, if that c value is bigger than 1, then it's going to stretch it vertically up and down. It's going to make it taller. It's going to stretch it more from top to bottom. It's going to stretch that range. Where if that c value is less than 1, okay, then it's going to shrink it. It's going to push it to more together from top to bottom. Okay, like if you put a aluminum can on the ground and you step on it, it's going to squish it, shrink it. All right. So what we need to do is just kind of get a little practice at this, kind of see how these all kind of work together, and we'll look at vertical stretching and shrinking first. Okay, so what we're going to do, here we go. We're going to start with this equation right here. Okay, and what I want to do is I want to create a new equation. This is C1. We're going to create a new equation called C2. That's a vertical stretch of this original one. Okay, it's a vertical stretch by a scale factor of 4. Okay, so what I want to do is I want to make it 4 times bigger vertically, from top to bottom. Okay, so if I'm doing a vertical stretch, okay, I got my vertical stretch, and I want to stretch it by a factor that's greater than 4, my c value is greater than 1, it's 4. We're just basically putting that number out in front of the function. So for my C2 equation, all I'm going to do is just take, because I want to stretch it, put a 4 out front of the function, okay, of that f of x. I should probably write the notation here, so give me a second. Let me change this. We'll go 4 times that function. That's what the c value. C value is greater than 1. It's 4, so I'm putting it out front. Then I can say 4 times what f of x is, which was this x to the third plus 3, and then you could distribute. Okay. So that is our equation. C2 equals this 4x to the third plus 12 would demonstrate a scale factor of stretching vertically at 4 times what this equation is. Okay, if I want to shrink it, okay, vertical shrink, I'm going to take the vertical shrink of the original one by a scale factor of 1/3. Okay, so obviously less than 1. Okay, so it's going to shrink this. It's going to squish it from top to bottom. So same idea. We're just putting that 1/3 out front of that function. So it'll be 1/3 of x to the third plus 3. So then if you distribute 1/3 x to the third plus 1 is our function that's now 1/3 the size of the original one. All right. Now, just a little practice, because I know this when we get to horizontal stretching and shrinking, this division, and if we're dividing by a number less than 1, we're dividing by a fraction. So I just want to kind of review some of the deals that we do with fractions. And, so just gets a little practice real quick with this. So this, if I look at this equation right here, or this expression, it's x divided by 1/2. So a lot of times you think about this as x divided by 1/2. And, what you would have learned a long time ago when you multiply or divide with fractions, you might have heard of the old copy dot flop. Copy dot flop when you're doing division with fractions. So what I'm going to do with this fraction then is copy the first one, put a dot here for multiply, because we're going to change that division to multiply, and then flop the second fraction. And so that's 2x. So this is the same as what this is. Okay, same idea. And if I want to take I've got something divided by a fraction, that's x divided by 2/3. So copy dot flop, and this would be 3/2 x. Okay. This is the same as that. Okay. So I want to use that in really helping you do some of the math a little bit quicker in these problems and not have to worry about that division piece. So let's go back. We're going to still start with that original function, that x to the third plus 3. And they want us to find the C4 function that is a horizontal shrink. Okay, so now remember up here, horizontal shrinking is a factor less than, the C value is less than 1. So I want a horizontal shrink of 1/2. So really what I'm doing now, because it's horizontal, I got to put it within the function. So I'm going to go f of x divided by 1/2. So again, that sometimes confuses people. They don't like that. It's just too much gibberish in there. So again, you do the copy dot flop thing in here, this x divided by 1/2 like we did over here. And this is, again, really the same as f of 2x. And that now sometimes makes it a little bit easier for people, because now what I all got to do is I got to just put 2x in for that x. So inside for that x is 2x. I still got to cube it, and then still have to add the 3. If I cube that, that's just 8x to the third, and then plus 3. And then there's our expression or equation, if you put the C4 up front, for horizontally shrinking this graph by a factor of half. It's half the size. It's half, when you shrink it, it's half of what it used to be. Okay. So same thing with C5. It says a horizontal stretch. So now I'm stretching this. So again, if I just look at the formulas, stick with the formulas up here. And this would be f of x. And I want a horizontal stretch by 4. So if it's a stretch, the C value is bigger than 1, which it is 4. This is just x over 4. Okay. Now we don't have any division by fractions anymore here, so what I can just do is I can just go right to putting that in there for that x. So this is just x over 4 cubed plus 3. And do the math here. This would be x to the third in the top. 4 to the third is 64 instead of the plus 3. Right. This is now horizontally stretched from left to right. It's made longer by 4 times. When I graph this, would be longer by 4 times than what that one was. Okay, let's practice this last one here. We're going to put them both together. We're going to put them both together for C6. It says a vertical shrink of C1, so we're going to go up here to original equation again, with a scale factor of 1/5. So a vertical shrink is just the number out front. So I'm just going to put the number 1/5 out front of our f of x. Okay. I guess I got too many parentheses in there. So it's not a problem, but it just looks messy. So 1/5 f of x. So that'd be the first part, with showing that a scale factor of 1/5. But then I also want a horizontal stretch. Horizontal stretch. So if it's a horizontal stretch, I'm up here. That means that c should be greater than 1, and that's what we're doing. We're doing a stretch of 7. And so again, that number is just going to go on the bottom. So I'll rewrite this as 1/5 f of x divided by 7. Because again, a horizontal stretch, c value is greater than 1. Put it down on the bottom. Should be ready to go. So now, what we got to do is going to solve this. We got 1/5 up front, so I'm going to take this x to the x over 7. That's kind of getting put into that x. Okay, so that would be x over 7 to the third plus 3. Now if I just do a little math on this, we got 1/5, and then this would be the x to the third. Now again, remember, this is 1/5 times all this. Oops. This would be x over 7 to the third is 343. That's still plus 3. So that's everything done inside here. But now I've got to just take and distribute that 1/5 to everything. So this would be, screw that a little bit. X over 5 times 343 is 1,715. And then plus 1/5 times 3 is 3/5. And there would be the count combined. And this is our C of 6 equals. That would demonstrate that this equation here, this graph. Oh, I'm sorry, I lost my third in here. How'd that happen? All right. This graph here would be, compared to this original one, is shrunk vertically by 1/5, but then stretched horizontally by 7 times. All right. Well, let's move into the last part. Last part here on translation, just moving it up, down, and left and right. Okay. So let's switch it up just a little bit more. There we go. So on translations, a little bit easier here. You might remember some of this certainly from advanced algebra, and when you had equations with parabolas. So we talked about something like y equals x squared being our parabola, and then y equals x squared plus a number. So let's just say plus c. All right. That's problems like this. Right? Those are vertical translations. The number I added here, or subtracted, is outside that x squared. It's outside the parentheses, like to say. So then that just moves it up or down. If it's positive, it moves it up. If it's negative, it moves it down. Where we had some other problems, they were like y, start with y equals x squared. And then if we had inside the parentheses, if I had something like x plus c squared, then what you had to do is you kind of had to think opposite. I always talk about, you had parentheses, think opposite. Think opposite. So normally you want to think, oh, this moves it, if it's inside next to the x, it moves it left or right. Then you would, again, think inside the parentheses, you would think opposite. So instead of going to the right c, you're actually going to the left c. And that's kind of what you see right here with the horizontal translations. That you can see when I subtract inside the parentheses, it doesn't move it to the left, it moves it to the right. When I add, it moves it to the left. But when it's not inside the parentheses, it doesn't affect the x. It's not by the x, so it moves it in the y direction. And then if you add, it does move it up. If you subtract, it moves it down, so it does the same. So let's take a look, how we might do this problem. It says here, describe how the graph, apologize, it's kind of small here. I guess I could probably just blow that up a little bit. You can kind of take a peek at that. It says describe how the graph of f of x equals x. So we know that that's just our normal absolute value problem. Could be transformed to move the graph of y equals absolute value of x plus 4. Okay. So, well, we know, again, this is outside the parentheses. It really kind of is parentheses. The absolute value kind of operates like parentheses. So that's going to affect the y because it's not in there with the x. And if it's not inside parentheses, it does it as is. So what this does is this just moves it up 4. This one down here, this is inside the parentheses. Right, this is inside the parentheses for absolute value. So you've got to think opposite. And again, it's inside by the x, so it's moving in the x direction, either left or right. People think plus, or no, the plus is moving into the right, but remember, think opposite. So this actually moves left 2 units. Okay. No, so let's look at this piece right here. All right. So what we're going to do here is just by looking at the graphs, we're going to tell, has it been moved to the left, to the right, up or down, and then write the equation for this. So as each view shows the graph of y equals x to the third, that's the cubic graph. So that's the original one with the red dotted one. Right? And then there's been a translation. Right? So if I look at this blue graph, right, looks like it's just been moved down 1, 2, 3. So this has been moved down 3. So I got to, if I move up and down, okay, that's not in the parentheses with the x. So I'm going to write this as y equals, or this is y sub 2 equals, and I've got the x to the third, because it's not moving left or right. I'm not doing anything inside with that x in parentheses. I'm just moving it down 3. This graph right here looks like it's been moved from here, 1, 2 to the left. This looks like it's been moved left 2. So when it's left or right, you got to put that change inside the parentheses with the x. And still keep the cube so it represents that same shape. But now remember, if it's inside parentheses, you got to think opposite. Left, you normally think it's minus. You got to think opposite, so this actually be plus 2. And then just kind of the other way around with this one. This one looks like it's starting here. This is moving 1, 2, 3 units to the right. So this one's going right 3. So if I'm going to rewrite this equation here, again, left and right, you got to keep it inside the parentheses. And again, think opposite. Right 3, you normally think plus 3, but opposite would be minus 3. All right, let's take a look at this one. So we've got a couple things happening with this one. So what we're going to do is end up trying to graphing this. You can kind of think about what's happened with this graph. This is an absolute value graph. The original parent function is that f of x equals absolute value of x. So we know what makes that v. You know it's going to be this v. Okay. But what's happened to it? Well, when I look here, this is kind of inside the parentheses with the x. So again, think opposite. This is moving it right 3. This one's outside the parentheses, away from the x. So it moves it up or down, and it does it as is, as you see it. So this would actually be -4, so that moves it down 4. Okay, so what I'm just going to do is I'm just going to take that original origin, point at that vertex, and I'm just going to move it to the right 3 and down 4. And because there's no slope change here in front, there is no slope. The number there is actually 1. That slope stays the same as it did in the original one. So it's just up 1 over 1, up 1 over 1. And same thing on this side. You can double check that, with a little XY table if you wanted to see if it works. You would have started off here. There's an XY table, and 0, 0 was a point on that. 1, 1, because I went up 1 to the right 1. I went up 1 to the left 1. So that'd be -1. 1 would also be points. But for this graph here, which represents moving to the right 3, so that you have to add 3 to every x. And here, that's moving everything down 4, so I'd be going y -4. We can look at all these values here. So if I look at that 0 and add 3, that'd be 3. Take up this y value and subtract 4, should be -4. So if I take this corner right here, 1, 1, add 3 to it on the x, that'd be 4. Subtract 4 from it, would be -3. Okay. And if I took the -1, 1, -1 and add 3, I'd have 2. And then subtract 4 from 1, and then -3. So you can even double check to see if those points are on there. Is 3, -4 on there? 1, 2, 3. 1, 2, 3, 4. It's right there. Is 4, -3? Well, 4, -3 is right there. And 2, -3 is right there. You can do more points and see that too, that it works. And here's our sketch of that graph. So let's get you to do a little practice on a couple of these problems and take these graphs and practice some translations with graph. Got to practice 10A and 10B. So go ahead and pause the video and come back and see how these were done, see if you got them right. All right, so you can see the answers now that you would have gotten or should have gotten. Notice again that this graph here was just that original parabola, and it's been moved to the left 1 and up 3. So kind of read the blue one here is the original one. The red one is the translated parabola. And over here, this is the logarithm. So remembering logarithm. Logarithms always go through 1, 0. So that's the kind of point you're going to use right there in moving it. So you can see that this has been moved to the right 4 and down 2. So it was right 4, down 2. And that, remember now that asymptote moved along with it too. So that's kind of lesson 1.4 in some of the single transformations that we have you do. So we get you to work on a little bit of a homework and get some practice before we hit lesson 1.5, where we'll do sort of some things like what we did with this one up here, where we're doing two things at once. So we're going to kind of put multiple things together. So that's it for now. And wish you skill on the next homework assignment, and we'll see you in the next video.